There's another famous problem that is closely related to the probability of coprimity. This famous problem is called the primitive circle problem. It states as follows, that the function c of x be the number of primitive integer vectors in the disk of radius x. M squared plus n squared less than or equal to x squared. And the GCD of Mn is equal to 1. Namely, each pair consists of two coprime integers. And this is precisely what we mean by primitivity. Analytically, we can also write this in another way, as a sum of ones over the domain where m, n are integers, m squared plus n squared less than or equal to x squared, and GCD equal to 1, which would be easier for us to estimate this guy. So the question would be, what is an asymptotic formula for c of x as x becomes large? The purpose of this lecture is to introduce an asymptotic formula for c of x using the same method we used in the proof of Merton's theorem, as well as an elementary estimate we derived earlier in the Gauss circle problem. To simplify our notation a little bit, henceforth, we assume that x is always a positive number and d is always a positive integer. Well, m, n, r, s are taken from z. So m and r, s could be positive, negative, or 0, but d is always a positive integer. Okay, we'll start with this definition of c of x. C of x is equal to this summation. And again, we're going to use our old trick, which is Theorem 2.1, page 55 of Apostol's Introduction to Analytic Number Theory, which will transform this sum into a double sum and introduce at the same time the Mobius function, mu of d. And this, whenever we see a double sum, we always have an urge to switch those two sums using Fubini's idea. So this guy, as we did before, can be rewritten as, the reason that we could make this change of variable is that we have the following 1-1 correspondence, as we did in the proof of Merton's theorem. The bijection is given as follows. By sending m, n, d to m divided by d, n divided by d, d. And this map G is bijective because it has the inverse, sending RSD in the second set back to RDSD D. And this bijection precisely justifies this change of variable. Okay, now let us further simplify this last term. An easy thing to do is that we can pull this mu of d outside of this first sum. And this first sum will be a sum of ones. We can pull this outside simply because the variables here are really r and s, while d is fixed. Okay, now, when you look at this, what do you see? If you look at this part, this is precisely the Gauss circle problem with respect to the radius r divided by d. So, let us employ the result from the Gauss circle problem, where you can find in another video I made. We're just going to use the most elementary result for the Gauss circle problem, derived by the Gauss himself. By the elementary solution to the Gauss circle problem, this part has an asymptotic formula, pi x squared divided by d squared plus big omega of x over d. And we'll multiply this guy by mu of d and take the sum. So this is by the Gauss circle problem, the most elementary solution. There are much more complicated asymptotic formulas for the Gauss circle problem, and I believe up to date, the sharp form for the asymptotic formula is still open for the Gauss circle problem. But in this video, we are just going to use this most elementary form, which we actually derived in another video. The next thing we want to do is that we want to separate this sum into two parts. The first part is pi x squared times the summation of mu of d divided by d squared plus the second part is the sum of mu of d times the big omega of x over d. Here actually I don't have to emphasize that d is greater or equal to 1. We assume that d is always a positive integer, so we don't have to put that thing. And now we'll play with them separately. The first part is something we have already done before in the proof of Merton's theorem. Let me remind you. In the proof of Merton's theorem, the summation over d less than or equal to x of mu of d times x squared over d squared has an asymptotic formula given by 6 over pi squared times x squared plus the big omega of x, where we change this finite sum into the difference of two infinite sums. And the first infinite sum can be calculated directly with the help of a theorem in Apostol's book, which involves Euler's identity. And the second sum has an asymptotic formula given by another theorem just in calculus, and you can also find in Apostol's book. So, we'll just apply the result we got earlier. And this first term will be equal to the pi times 6 over pi squared times x squared plus the big omega of x. And the second part can be estimated as follows. So this second part, at the absolute value, this will be less than or equal to, if we majorize this mu of d to just 1, because mu of d's absolute value is always bounded by 1. And this big omega of x over d will always be bounded by a constant times x over d. And remember, this constant should be independent of this ratio x over d. Actually, here we have a little bit of subtlety in here. And to be absolutely rigorous, we need to go back to the proof of that asymptotic formula for the Gauss circle problem, because this big omega came from that Gauss circle problem. Remember, in the Gauss circle problem, we derived the formula for the case when r is greater than square root of k. So the arrow term will be a constant multiple of the radius when r is greater than square root of 2. However, you should realize that as long as r is greater or equal to 1, this arrow term can always be bounded by some other constant times r. As long as this r is not too close to 0, it doesn't matter for us to state that this guy is always bounded by some constant multiple of r. That is precisely what we need in this primitive circle problem. The reason that I mentioned this subtlety is that in our case in here, d is chosen to be less than or equal to x, meaning that d can be really close to x. In the extremal case, d can be equal to x, so that this guy becomes 1. But in general, this asymptotic notation makes sense only if this argument becomes really, really large. It may not hold in general that this guy is bounded by some constant multiple of this argument. But in this special situation for the Gauss circle problem, we can actually see that this holds as long as x is greater or equal to d, or x over d is greater or equal to 1. That is the subtlety in here. If you understand this part, the rest won't be too hard. So this will just be c times the summation of x over d, and you can even pull this x outside and just look at the summation of reciprocals of d. And this part has another asymptotic formula in a postdoc's book. Or you can find this in many books on calculus or real analysis. So this part will be log of x plus some constant c prime plus big omega of 1 over x. And if you combine these, this will be c times x times log of x plus some big omega of x plus big omega of 1. And now you can plug all of this back to here. So the second part will be like a big omega of x times log of x plus big omega of x plus the big omega of 1. And now let us simplify this. Pi times 6 over pi squared will be 6 over pi, and we multiply this by x squared, and we combine all the others. The one that has the fastest growth is the big omega of x times log of x. So this is the asymptotic formula we obtained for the primitive circle problem. Let us summarize this. The number of primitive pairs inside a disk of radius x will have an asymptotic formula 6 over pi times x squared plus the big omega of x times log of x. And this is the end of this video.